There are some topics in quantum computing that make people ask, what does it actually do? And after reading an article or watching a video about it or looking it up in a proper textbook, the question is still, yeah, but what does it actually do? And the quantum Fourier transform, or QFT, is a really good example for this. The standard way to teach the QFT is something along those lines. Step 1. Define the classical discrete Fourier transform. Step 2. Write down the QFT formula and/or matrix. Step 3. It's kind of the same, just quantum. Step 4. It's very important. And this might even make sense in some cases, but more often this is like explaining something you don't know by something else you don't know. Also, explaining the QFT only through the lens of the classical Fourier transform easily leads to people missing the point. So, above all, I will try to answer the following questions in this video. What's the big deal about it? Why does everybody say it's important? What problem does it solve? i.e., what are the applications and use cases for it? And of course, but what does it actually do? It's an old pun that the Fourier transform is called a transform because it was so transformative. It truly is one of the most important tools in signal processing and engineering today. Basically, the discrete Fourier transform, or DFT, calculates which frequencies make up a signal, while the fast Fourier transform, or FFT, does the same, but dramatically faster. Beyond audio and video processing, Fourier transform are essential in technologies such as Wi-Fi, 5G, and data analysis for things like radar, MRI, or even astrophysics. And yes, there is also a version of the Fourier transform for quantum computing, consequentially named the quantum Fourier transform, or QFT. And as many quantum algorithms, it has a huge advantage, but also a gigantic drawback. The QFT is essentially an algorithm for finding patterns in the phases of quantum states. And while these are somewhat similar to frequencies of sound, for example, they're also different. So first, we need to properly understand what phases in quantum states are. We could take any quantum state, but as we're talking about quantum computing, let's consider a qubit. It has two basis states it can be in, and each one of those has a so-called amplitude. Whenever you measure a qubit, you will get either 0 or 1, and the amplitudes determine the probability for either outcome. You need to take the norm square of each amplitude to get the respective probability for each outcome. So, for example, this state means that you will measure 0 70% of the times and 1 30% of the times. And that's the precise meaning of the rather vague statement that you often hear that qubits can be 0 or 1 at the same time. You will only ever measure 0 or 1, but each qubit has a certain probability to be either. So that is the amplitude, but there's more. Each amplitude is not just a number, but a complex number. And I'm not going to start with square root of -1 and all that. We're only going to consider it geometrically. And geometrically, a complex number is a number with a length, which we call the magnitude, and also a direction, defined by its angle, which we call the phase. Note that seemingly regular numbers like +1 or -1 are also phases. An angle of 0 is just +1, and an angle of 180 degrees gives you -1. And the reason why phases in quantum mechanics are often misunderstood or straight up ignored is that by themselves they have no effect. Because when we calculate the norm square of an amplitude, the length always gets squared to give some number, but the norm square of the phase is always just 1. So whatever phase a single quantum state may have, it has 0 impact on the measurement results. This state, for example, just means that both 0 and 1 have a 50% probability, and this state has the exact same probabilities. We could not find out any difference between these two states by making measurements. So while these states are different mathematically, they seem to be identical physically. Well, there is one thing though. Now, as we said, by itself, a phase makes no difference. But as soon as we add two states together, a process called interference, they very much do. If we take the two states from before, which we couldn't distinguish by measurements, and add them together, the result is completely different to the addition of just two copies of the first state. So there is information in the phases of quantum states. It's just very well hidden. In fact, it requires interference with other quantum states to even be visible. And that's why we differentiate between a global phase of a state and a relative phase. A global phase is just a common factor we can factor out of a single state. This global phase never makes a difference. A relative phase is a phase difference between two states, either different ones like here, or the same ones like here. Also note that what is a global phase for single states will become relative states as soon as you add it to something else. But that's almost putting too fine a point on it. All we'll be interested here are relative phases. These are the ones that make a physical difference. Okay, so the idea behind any form of Fourier transform is always this. Any function or any signal can be built using just sine functions. You just have to add up enough of those of the right frequency and size, and you can reconstruct anything. Technically, you will almost always need an infinite amount of sine functions, but in reality, a large number will do. What the Fourier transform does is it lets you calculate which frequencies are contained in a signal and with which strength. This information can be visualized as something like this. You can also track this over time, then you get a more complicated plot, a different frequency plot for every time step. And broadly, all of this is also true for the quantum Fourier transform, but what frequencies is the QFT calculating? Like, what exactly is oscillating here? A quantum state isn't the same as an audio signal. That's where we come back to phases. Let's consider this 2-qubit state, for example. Remember, these numbers are phases, and they are numbers with a direction, an arrow. If we draw the arrows for these phases, we see it rotates with a certain frequency. We call this the winding of the phase. And the QFT calculates exactly this, the frequencies of the winding of the phase. It takes this phase information and writes it into the amplitudes of new basis states. We can therefore use the QFT to transfer some information about the state's phases and put them into the output state's amplitudes, where we can measure them. And this way we can make the invisible information in the state's phases directly accessible. For example, as we saw, the states plus and minus give the exact same measurement results. All we get is 50% 0 and 50% 1. But we can never tell whether the phase is +1 or -1 or anything else. When we apply the QFT to the plus state, we get 0, and the minus state is transformed to 1. So after the QFT, we can easily measure this phase information. As another example, back to the 2-qubit state we considered before. Remember, this was just a single phase winding frequency, so the outcome of the QFT on this state is a single sharp outcome state. This tells us there is only one frequency, and we can calculate it to be 90 degrees. All of these examples might seem a bit simplistic, because they are, but they do get across the point of what the QFT does. It transforms the input state in such a way that the hidden phase information can be measured. And this is what the QFT actually does. Now, this might still seem a bit abstract, or you might question what this is even good for, and fair point, this is not necessarily obvious. But the thing is, we sometimes have states where we are very interested in the phases, like with quantum phase estimation, or we can artificially create them ourselves in a computation, for example in Shor's algorithm, which is the one that cracks all the code. So yeah, remember, step 4. It's very important. Okay, before moving on to the applications and significance of the QFT, let's look at its quantum circuit. For all qubit-based systems, we can rewrite the QFT to a simple product form. More specifically, we can rewrite the fraction in the exponential to fractional binary notation, which directly implies a very simple circuit for the QFT. Let's write this down explicitly for 3 qubits, for example. As we can see, this includes a lot of terms of this form. For the simplest, we only need a Hadamard gate. For each additional digit, we need an additional phase shift gate, which creates exactly the phase factor we are looking for. And even if you know nothing about quantum circuits and quantum gates, you might notice that there's only a very small number of them here. In fact, the QFT only requires on the order of n squared gates, where n is the number of qubits. And this is another significant fact of the QFT, because the classical discrete Fourier transform requires on the order of 2 to the 2n operations, and even the famous fast Fourier transform requires on the order of n times 2 to the n. So the QFT is exponentially faster. Unfortunately, there is a caveat here. And just so you know what we're talking about here, if the QFT actually brought an exponential speedup to Fourier transforms, the investments in quantum computers would be higher than the Manhattan Project and the Apollo program combined. And we would already have quantum computers since 2008 or something. So clearly, the exponential speedup isn't real. Well, it is real, but it's not usable. And this is one of the most important and misunderstood points in quantum computing, so I will make it here in full. The huge advantage of quantum computing is that it's all in there. The giant problem is that we can't just get it out. Now, let's assume that a quantum computation, any quantum computation, doesn't have to be QFT, creates this output state. These are the amplitudes, or rather the norm squares of the amplitudes of the different basis states. And this is the description of the state. This is what we would need. But when you measure the state, you don't get all those numbers. You don't even get a single one of those numbers. All you get is one random basis state, as the amplitudes norm squared determine the probability to measure each state. So only when you perform a lot of measurements, you get an idea of what the entire state looks like. So yeah, we can calculate the Fourier transform exponentially faster on a quantum computer, but we also have to run the calculation exponentially more often just to get at all the amplitudes. Because it's the amplitudes where all the information about the Fourier transform is stored. But the good news is that we do not have to run all of these exponentially many calculations for quantum computers to be useful. Whenever we're not interested in all the exact amplitudes, but only in a global property of the state, we can often achieve that with much fewer measurements. For example, when those peaks appear at a regular interval, we can efficiently find out this interval without exponentially many measurements. And this period finding is actually the core of Shor's algorithm, the one which lets quantum computers break RSA encryption. But more on that in my video about the Shor algorithm, which is supposed to be out soon-ish. I am Chris, and this is Physics But Awesome. At the moment, I mostly do stuff on quantum computing, quantum mechanics and cosmology, so if you like this video, subscribe for more.